a random walk. So run applause for Ben, please.
Right, so, well, I made a commitment that I would do my slides in a random order. I haven't actually seen what order they're going to be in. This could go spectacularly well, and it could be terrible. I've got a couple of slides at the front that I know are coming up, so we'll go for those first. Oops. How do I go to the next screen? No. No. I'm on the last one. Oh no, I just saw what's coming up. That's better. So just a quick thought, what is randomness? Well, really we're talking about something like a lack of predictability. When you throw a dice, you don't know what the number that's going to come out is. Now that doesn't mean that there's a lack of order there, because if we roll a dice over time, we can predict what the aggregate results will be. But we have no idea on the 1,000th throw, no matter how many times we've thrown this dice, what the 1,001st throw will be. So that's getting somewhere towards a definition of randomness. Also, we may be talking about lack of bias. And there we're thinking of things that could affect, things external to this process that could affect it, that sway it one way or the other, things that we can control. So a lot of this is about kind of perception and control. And the final thing, when I was doing this slide, somebody said to me, oh, I've just done a presentation, I've got some pictures you might like to use. I was like, okay. Do you have a picture of a monkey rolling dice? And she said, yes, which I thought was quite random. We'll see if that comes up later on. Why is randomness interesting? Well, one reason it's interesting because I think we're in a sort of age where we can stumble across things that are interesting, things that are just good enough. It doesn't have to, I kind of think of, we tend to write code very deliberately, very logically, and if you asked what we did, it would probably be of the order of logic or of the order of maths or something along those lines. We think of it deterministically. But actually in life, we're relatively light, and we wander around and we see things, and the internet's a bit like that. I mean, do we really think that Google gives us deterministic results? Well, on one level they probably do, but on another level they're just results that are good enough. So there's an element of randomness that I want to kind of emphasize there. And the other reason randomness is interesting is because it's psychologically interesting. Sometimes it makes things easier for us to reason about, and I hope that some slides will come up later that demonstrate these points. Sometimes it makes things very hard and very frightening to reason about. So people are justifiably probably scared of concurrent operations and multi-threaded stuff and threads and locking and all that kind of stuff, because on some level it seems random, it seems out of our control. But hopefully some slides will come up that show us that actually randomness can make things easier for us to reason about as well. We'll see. So this is the way I randomized the slides last night. I did think I'd write some fancy program that drove my keynote with Apple script or sorted the HTML things. But in the end, I just got it, I automated the thing I knew that could do it, which was myself. Using a bit of Ruby. So I ran this thing and it told me which slides to swap, and then it told me which to delete a certain number of slides. Which means that after this slide I have absolutely no idea what order this presentation is going to come in. But hopefully if you keep these themes in mind, we should be able to get some sense out of it. I don't know, we'll try. And this is a little bit like the reverse of what Apple is doing with the iPhone. Instead of shouting at it, the computer kind of shouted at me and told me what to do. I quite liked it, actually. It's good. Oh, entropy. So this is the first random slide. So entropy is a measure of information that's in a system. If we toss a coin, there's one bit of entropy because it can be either heads or tails. We toss it twice, there's 2 bits. 2 to the power of 2, there are 4 possibilities: heads, 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 tails, tails, heads, and the 4th one, which I can't remember what order I did things in. The entropy of English text, and it depends how you measure it and which corpuses you take and so on and so forth, is somewhere between 0.6 and 1.5 bits per letter, which is really interesting. That means to pick out, for example, a 6-letter password, you're looking at something like, if you've picked that password from English text with the same kind of frequency as English text, I know there's a lot of things there, but you're looking at somewhere between sort of it being 1 in 10,000 to 2 to the power of 9, 1 in 2 to the power of 9 to guess what that password is. So that kind of gives you some idea of that. This isn't a particularly useful slide to have first. Oh, this is a better one. Does anyone remember the BBC Micro had a game called Elite, in which there are still a few people who are old enough to remember that who haven't died or gone to do Java or something. That gave the illusion of an enormous universe that you were flying through with planets here and there. It seemed to have a certain amount of stability. The planets seemed to be of a certain type. And when you came back to the game again, it was of a certain type, but it didn't have a lot of data in the game. The BBC Micro wasn't big enough to contain the data structure for that whole universe. Instead, that universe was randomly generated using not randomly generated, but deterministically generated using the random number generators that were built into the machine. So this illusion of randomness was given. And what I've done here is an illusion of infinity was given when, in fact, it was a deterministic, very compact, space-compact algorithm that did that. Now, I looked on Wikipedia and I found all the names of the planets in the Star Wars books, novels, and so on and so forth. And I went through and calculated the likelihood of each letter following each other letter. So looking at the table, in the names of the planets from the Star Wars universe, in the second row there, if you're on an A character, there were 9 planets for which the next character was then B. There were 7 planets for which the next character was C. And we can use that to then randomly generate planet names, which is what I've done at the top there. And they actually, it looks like gibberish, but then a lot of these planet names do look very much like that. The citizenship test. So this is an example of how I think you can use randomness to make things a bit more tractable. People are asked to take, people applying for British citizenship have to undertake a multiple choice citizenship test. It's quite hard to say. That has a number of questions. There are 4 options per question. The pass mark is actually 15 out of 20. I've put it here as 10 just to make the numbers a bit easier. And you could work out, if you filled that test in by random, how many people would be walking around who hadn't really passed the citizenship test. I don't think anyone really can because the questions are so obtuse. And you can work that out. You can use your binomial theorems. You can use your fancy maths and all that kind of stuff. Or you can write a few lines of Ruby, simulate it, and run it lots of times. And that's what I've done here, partly because I can't really do the maths. Actually, I did do the maths, and the maths comes out as about 1 in 72. But this is an example where the kind of repeated random simulation gives you some kind of handle on a mathematical process that maybe you find easy to simulate because it's closer to the real world, but you find the maths is something you don't know, or is harder for you, or you just don't know where to look. So simulation can be a really useful and easy way to simulate this stuff. And this is really a kind of a Monte Carlo method, and maybe we'll talk a bit more about that if the slides come up. Oh gosh. So this is the second slide I have about simulated annealing. Right. So let's talk about annealing to start off with. Annealing is a process that it's a metallurgical process. So when you're making a sword, as I know we often do, you might want, there are various imperfections in the crystals of the metal. And one of the ways to get rid of those imperfections is to heat up the sword and then slowly let it cool down. And as it cools down, you get a better chance of larger crystals forming. The idea is you increase the temperature, you increase the chaos, the energy in the metal. It pushes things around. Things are able to move more freely. And then as they cool down into a lower energy state. Simulated annealing is a metaphor for doing that kind of thing with computer processes. So in this case, the diagram is showing a ball on a landscape. That could be anything. The ball is just where we are currently. We're trying to find the lowest point on that landscape. And it's relatively easy to work out how to get to number 1, because you keep going and it goes down and then suddenly it goes up again and you go, oh, well, I'll stay in that local minimum. Number 2 is relatively easy as well, but it's kind of hard to get to number 3 because you've got that big jump from number 2 to number 3. I'm not sure if I'm making any sense here at all. But if we were to increase the energy in this thing by shaking it, if we do it enough, there's a good chance that the ball will jump over and end up in number 3. And this is what simulated annealing is, an algorithm for increasing the amount of randomness in a model that you've got, with the hope that once you stop, well, actually not with the hope, but once you stop shaking it, it will settle in to a better solution for that than you previously got. Now, it does take a long time, and but it's a useful application of probability and randomness in order to search a big search space that you're not necessarily able to understand with numerical techniques easily. Okay, and a bit of a jump. How do you select a random row from a database? So the naive way is to, which I'm sure I've done many times, which is to do select from users. We're selecting a random user here. Order by rand, that probably should have brackets after it because it's a MySQL function. Limit 1. The problem with doing that is you have to calculate that random number for every row in the table. And that causes MySQL to do a full table scan, and it's very inefficient. If the IDs in the table, if you're using auto-increment IDs, this is Murray's fault that he asked me to put this slide in, I think, if I remember rightly. It's probably the only practical thing in the talk. It's quite good. If you're using auto-increment IDs and you know there are no gaps, then you can just calculate a number out of band and go straight to that ID, which is what we're doing in the second table. But when you're trying to calculate something where you've got an extra condition on that, you obviously can't do the second thing. Or you've got gaps in your IDs, or so on and so forth. So then what you're probably trying to do is use subselects to cut down the number of rows that were returned, and then use the naive method on that subselected row, on that subselected table. Does that make any sense? Anyway, you probably, if you're using the top one, you should probably go on Google like I did and find other ways to do it, I think is the answer. Mutation testing. Does anyone know what mutation testing is? A couple of people. So mutation testing is a technique that takes your code, goes through your code and mutates it. And what it means by mutating it, it means, for example, you might have if something is greater than something else. Well, the mutation would be to change that greater than to less than. You might wonder why you would want to randomly change logic in your code like this. Well, if you change the logic in your code and then run your tests and they still pass, you've got a problem. You've either got a bit of logic that isn't tested, or you've got something meaningless happening in your code. So there are a couple of libraries that you can use to do mutation testing in Ruby. I don't think any of them are particularly good. I don't think it's a particularly well looked at field, and I think it's harder to do in Ruby than it is in a language like Java, where you can actually mess directly with the bytecode and do this stuff. But if you want to look at Heckle, or you want to look at Chaser, they can be a useful way of seeing if your tests really do have meaning or not. That's kind of the overview of mutation testing, but that's not why I put this slide in. I put this slide in to kind of to capture some of the fear and psychology to do with randomness and things changing that you don't know about. Just to look at the way these projects describe themselves. Heckle describes itself as sadism. That sounds pretty bad. And Chaser is declaring war on your code. Now, I think they're quite extreme things because they go in and change your code. But there's something about the fact that they feel random and uncontrollable that drives these extreme ways of thinking about things. And there's something interesting there, kind of a psychology of not being in control, which is kind of similar, of yielding control to these tools or attacking your own code with these tools, that is similar to, I think, how we think about randomness. And hopefully we'll see some more examples of that. Oh, random deployment. It's really good that this is followed because it kind of follows on. I've always wanted to try this. I think people who I've worked with in the past would have probably not let me do that. And the reason I want to try it is I think there's a psychological import beyond the import of never deploying or only deploy when someone says or deploying every time. There's something fundamentally different about when you check in, it will deploy maybe. I want to kind of, it's kind of a bit of a thought experiment. It kind of ties into, I remember Roland talking, was it Scotland on Rails, about the way we should experiment with code. We should, and this is a bit of art that could probably change you. What would it feel like to press that button, to check in, to type that, to press that return button, knowing that, not that it's going to deploy, and not knowing that it won't deploy until you sell someone, but knowing that it might. And I'm kind of interested in it as a thought experiment. I might try it and see what it feels like. If anybody wants to try it too, I'd really like to hear.
Random rollback.
Random rollback, yeah. That's quite good. Make it really hard to deploy sometimes. The kind of flip side of that is I think most places work like this anyway. Oh, this is a brilliant book. This is a book full of random digits. There are 1 million of them. And I got on a bit of paper here, I've got some facts about it. Oh no, maybe I've lost that. Anyway, oh yeah. So this was first published in 1955, when actually it was really difficult to get random digits, and it was very popular. Lots of mathematical things. You want a book of random digits. You want to avoid bias. Lots of game theoretical things and so on. One of the nice things about this book is that people have started reviewing it on Amazon. And this is one of the reviews there where it's a nice enough story, but the author needed a twist at the end. I could tell halfway through the book where the story was headed, which is of course, absolutely not true. The other thing about it, coming back to what we said about entropy earlier on, this book is probably the only one that's absolutely guaranteed to have no information in it, which is kind of odd. You can still buy it. They re-released it a few years ago. I don't know whether it's a bestseller, but if you go on Amazon and you're short of a few million random digits, you can buy it. They generated with an electronic roulette wheel. Using, I think they were using fluctuations in the bias of a particular transistor that the RAND Corporation had. So it's real, proper random. We might talk about that a little bit as well. Monte Carlo simulation. So I talked a little bit earlier about simulations and how they can make things a bit more tractable. Monte Carlo techniques are repeated random sampling of a particular function, and then averaging those out to maybe find the minimum and maximum that you expect, and so on. It was a technique that was interestingly invented for the Manhattan Project when they were simulating nuclear bombs. And they called it Monte Carlo as a code name, believe it or not. This is a really, really simple Monte Carlo thing that estimates pi. You can try it. It's based on the diagram up above and the fact that if you randomly draw dots in a square, and that if you count the ones that which are more than 1 unit distance away from the origin, the ratio, if you count the ones that are less than 1 unit distance away from the origin, the ratio of those to all the dots will give you an estimation of pi because of the ratio of the area of a square to the area of a circle. But it works quite well. It's quite a useful way of envisaging this stuff. And a really useful quote from von Neumann, who came up with these things as part of the Manhattan Project, was once he started to run the simulations, even though he understood, knew, and had invented some of the maths and trusted it implicitly, seeing the simulation data come out gave him confidence. And that's really interesting because that kind of confidence coming from random sampling as against the fear that the uncertainty of randomness can cause in us is, I think it's quite interesting. You find a lot of people using Monte Carlo simulations, for example, in stock exchanges, in banks and in traders, where they've got huge banks of computers and they don't really know what to do with them and they don't really know how anything works. But if they run lots of stuff, they can justify the trade they're going to make because of the hormones that they're going through their brains and the cocaine. I don't know what this slide's about. Oh, yes, I do. Yes, I do. So a couple of times in my career, I've come across the situation where you've got a queue of work to be done, and that work gets handed off to distributed workers to process. In one case, it was orders that had come in that needed then to have credit references checked against them. The credit reference bit was done out of band. If it took a day after the order, that was fine, but they were all kind of worked through one at a time. And the system that had been created was incredibly complicated because, so an order came in, and then it needed a flag to say whether the credit check reference had been sent to the credit check reference program. But that wasn't good enough because then the credit check reference program had to acknowledge that it had received the message. So it needed another flag to do that. Then it had to wait, and then you needed a batch process to run every so often to see whether any of the things that it had sent out to the credit reference program that it had acknowledged were going to come back. And it just gets really complicated with all the locking and the queuing and the rest of it. And there was a really simple solution. It didn't matter if some of these things got processed twice. So all we needed to do was keep throwing randomly credit requests for credit references to this program. We didn't care whether it received them or not because randomly we were going to send it again if it didn't get processed. And as long as if you relax the requirement that no message is processed more than once, you can save an awful lot of time by just randomly throwing stuff at distributed processes and not caring whether they've received them, whether you've sent them or not. And you can calculate, really quite easily, given the amount of time it takes for these processes to work, the number of processes you've got, what the chances of something being processed more than once. And it tends to be quite a scary thing to implement because you're writing quite high-value code and you're putting, and randomly send some stuff. But it does work, and it removes a hell of a lot of complexity from some of these distributed processes if you can fire and forget and keep firing and not have to monitor this stuff. I've come across it a couple of times in my career, and it was every time we did it and just relied on, theoretically, it's possible that there would be something that was never picked and stayed in the queue forever. But in practice, it doesn't really happen, and it's quite a useful technique. True random number generation. It turns out that true random number generation is quite hard. Randomness is quite elusive, or at least it's hard to find efficient ways to generate random numbers. But there are several ways of doing it. In fact, there are many, many more ways, but these are some of the common ways that are used. Shot noise, which is to do with the bias in electronic equipment and the noise that you can pick up from there. Nuclear decay. We're doing this all the time in our it sounds really scary, but probably every smoke detector has got a nuclear source in it that you could use to do this. Photons traveling through a semi-transparent mirror. You can't tell in advance whether it will pass or not, so that can be a source. RF noise, random.org, which is an organizer which you can go to on the web and has various APIs for you to get true random numbers from, uses atmospheric noise and RF, which is great, but it's actually easy to intercept. It's easy to actually send a signal down that when people were expecting noise. Thermal noise, all the electronic components are slightly noisy. They change with their heat and so on, and you can measure that. And clock drift as well. That's quite a common way of getting hold of real random numbers. There are sources of real random numbers on the internet. I mean, the chances are, if you really need real random numbers, you probably shouldn't trust a site on the internet that's giving them to you. But you can go to Hotbits, or you can go to random.org or various other places and just get a stream of random numbers if you want. You know, 5 minutes. Okay. Oh, this is Ernie. Ernie's the machine that generates the numbers for the premium bonds. Premium bonds were a clever way that Harold Macmillan came out of to get people saving in the 50s. So you can buy premium bonds, which is a way of lending money to the government, and instead of them paying you interest every year, they put all that money into a prize draw and pick premium bonds every month, and you may win £1 million after investing, I don't know, 10 quid or whatever. But premium bonds were and still are really important. But when they were invented in the 50s, I think it was 1957, they didn't really know how to generate the random numbers to the level that they needed them in order to guarantee that this was fair. And they were worried about people gaming it and so on and so forth. So they built this thing on the left, which is ERNIE, which is electronic random numbers. And it was actually cobbled together from bits of Colossus. And it was the same team that did that, although nobody knew that until the stuff was declassified. Colossus being the code-breaking machine, one of the code-breaking machines that they used at Bletchley Park. And it ran for 16 years. The biggest problem it had when it launched was it generated numbers more quickly than the teleprinters of the day could print them out. And if you look, I've got you should go and Google for some images of this, because next to ERNIE were banks and banks of filing cabinets in which were the premium bonds that people had bought. And when the numbers came out, people would scurry along to see if they could find the things on. Eventually, they replaced it. I think that's ERNIE 2 or ERNIE 3. We're on ERNIE 4 now, over there on the right, and they decided to style it up somewhat. But ERNIE 1 used signal noise from neon tubes. Now it's just, rather disappointingly, just a card that goes into some PC that's manufactured for the Cryptography Institute. But then this was a real custom, difficult thing to build. Yeah. And every month, apparently, they go and they check whether it's still random. I don't know how they do that. Oh, this is another fantastic machine. This is the bean machine. And this was invented by Francis Galton in the 19th century. As you drop beans you drop ball bearings in the top, they bounce around, and they drop down into one of the various slots. And they tend to show a distribution there, which is really familiar. What's interesting about this one's in an investor thing, and the line on there is not something mathematically generated. The line on there is the variation in stock returns that they've had every year. So the best predictor of whether, amazingly, given this incredibly complicated system with people doing trades and companies coming and going, thousands of people involved, lots of small trades, lots of big trades, lots of fluctuation in the market, it's still best approximated by a machine dropping ball bearings into tubes, which is amazing, amazing. It's kind of, yeah. Anyway. Damn you autocorrect. I'm not even going to say much about this other than, yes, this is what happens when you use statistics to generate text. Oh, this is the random number generator from random.org, picture of it. I think the whiskey is important. I'm not really sure. But these look like the kind of people you want to get your random numbers from. Genetic algorithms and space invaders. Have I got time to talk about this? Years ago, I wrote a Space Invaders program where the Space Invaders were driven by a genetic algorithm. What that means is it's an algorithm that they had some kind of genetic code which you fed in. So you imagine a black box that you fed in some numbers here, and out came whether it should go left, whether it should go right, and whether it should fire its little gun. And the Space Invader, the interesting thing is every time a Space Invader got killed, we bred a new one from the ones that were the most successful that we'd come across so far. So the idea is that the population as a whole grows some algorithms and becomes smarter or become better suited to the environment they're in. The reason it's interesting is because one of the things I had was a cost function, which is that every time the Space Invader fired a missile, it would lose some energy. When it lost all its energy, it would die. And I switched it on and I left it running overnight. This is kind of 15 years ago and in Java. So I left it running overnight and it had more or less compiled. No, I left it running overnight. It went really slowly. But in the morning I came down and the Space Invaders were firing all the time. And I couldn't make any sense of that because my cost function should imply that they should have minimized the amount they were firing. But it turns out that there was an integer overflow bug, whereas if they fired an awful lot, it would reset their costs to 0. And the genetic algorithm had found that in my code, and I was happy as anything. Netflix have a thing called the Chaos Monkey. And the Chaos Monkey is a demon, a monkey demon, that runs on their servers and randomly kills processes. And again, that's interesting. It's interesting because it's random. It's a way of them making sure that their things are robust, but there's something psychological about it being random that it makes it slightly more fearful to us that it's doing this stuff. If it just went through and killed processes in order, maybe it would achieve the same effect, but it wouldn't be a chaos monkey. It wouldn't have that same random primordial fear that we have of the kind of chaotic. Pseudo-random number generators, we've probably already talked about those. The 1969 draft lottery in the States, this is about how randomness and bias is quite important. This was the lottery that was used to send young men to Vietnam, and it turned out to be biased. It turned out that if your birthday was in the early part of the year, you were much more likely to be chosen than the latter part of the year. And there were obviously very big court cases about this, which came to the conclusion that because you didn't pick what part of the year you were born in, it was probably okay. So, yeah. Which is actually, it's probably quite fair, I think. Oh gosh, how many more slides are there? Newtonian Casino. Has anybody read this book? It's a fantastic book telling the story of a group of people, a group of graduates at MIT, I think it is, who decided to try and measure the bias on roulette wheels and outplay the casinos. And what they did, they made tiny little computers that they could fit in their shoes. They went to Las Vegas and counted revolutions of the roulette wheels. And eventually, if you do that enough, not very much, and you have smart enough programs, you can detect enough bias in the roulette wheels that you can generate yourself a profit. And it's a fantastic book about how this 5 or 6 year project went on, how some of them got electrocuted while they were at the table because the thing short-circuited in the shoes, so they didn't really realize how waterproof they needed to be. People got badly burnt, but they couldn't leave the tables because then someone would have known that they're trying to cheat. It's a terrific thing about a kind of a big tech caper that happened in the late 70s, and it's well worth a read. But it shows that even roulette tables have biases. They can be detected, and you can use that to go up. Bloom filters. I probably haven't got time to talk about this. I'll be really. Oh, there we go. We're done. Oh, there were some really good ones you didn't get to see. But that's it, really. Consider randomness as a tool that you might use to give your programs a statistical chance. Consider it as a way of modeling things in order to make them more tractable than maybe the logical way or the mathematical way or the provable way would do it. Consider the psychology of randomness, and please do lots of experiments to see whether random deployment is as frightening as I think it might be. Thank you.
It would be fun to somehow randomize the questions, but I don't know how to do that. So does anyone have a question for Ben? Right at the back.
Thanks, Ben. How do pseudo-random number generators work? How random are they? I think just standard stuff we have in a computer.
So it's not necessarily how random they are. It's more how often, what the period is, really. It's basically just a mathematical function that you ask for the next number, the next number, the next number. And if you know the function and you know where you're starting from, it's entirely deterministic. And they tend to be designed for efficiency as well. So it's relatively easy to work them out. They're relatively simple functions that just generate, and the difference in them is the periodicity. If you've got one that for which the period is every 1,000 numbers it repeats, well, that's not really that useful. Or it might be. Maybe you can find a way of using that. I don't know.
Don't they seed it with a microsecond bit of the clock?
They do, but it still depends on how that seed translates into. If your random generator has the same periodicity as microsecond resolution, then okay. But if it's less than that, the seed's going to effectively, it can only point you to a certain step of the.
Just multiply it by a factor, whatever.
Yeah. I did have a slide with some maths on about it, but I deleted it. It's quite good because I didn't really understand it.
Thanks so much a question, and as a follow-up on that, if you use Ruby's random number generator, the periodicity is 618.
Okay.
Which is really, really bad. So if ever you want to do a lot of random number generation in Ruby, generate new seed values less than every 618 times you use it.
Okay.
And it uses an algorithm called mercy and twist, which is just one of the most notoriously easy to predict. But happens to be really hard to implement. So don't do random numbers that way in Ruby. But if you ever need them, the OpenSSL library has a ridiculously complicated, normalized, very high periodicity random number generator that's not documented in the Ruby Manor. So.
There you go.
For your Space Invader game, could the aliens take input from the position of the ship?
Yeah, I think so.
So they were responding.
Yes, yeah, because they used to kind of the kind of formation that most of the generators used to kind of form a kind of diagonal line which kind of responded to how the anyway. Yeah, I think so. It wasn't a very good program, but I only brought it up because it was a bit genetic.
This isn't necessarily just for you as much, because I regularly find reading in the documentation of a database, I don't remember which one, that is actually a special case ordered by RAND to do it properly, because it's is a common access pattern on Dash.
Oh, brilliant. Use order by round.
But I can't remember what it is and whether it's classical or what.
Right.
So I don't know if you will know.
In general, it's just really hard because that's not what databases are designed to do. So it's going to be inefficient for everything.
On the by random, if you just use the floor, you always want less than maximum bit. You sort by greater than or equals to. Sort by that bit.
Yeah, and then you don't get the gaps in it. If you've got as long as it's So if it's if your key space is evenly distributed, even if there are gaps, you can use a greater than there rather than equals, and as long as it's limited to 1, it'll work the same way. But you've got to make sure that the keys are evenly distributed and the likelihood of a gap is popping up if you want it really random. I think is that what you meant? Yeah.
Any more? No, thank you very much again.